1, 2, 3, 4, test, test. Lala. Okay, so let's continue. Since the question popped up several times now, yesterday and today, we've decided to put in a couple of slides from our lecture. You see, it's very recent. Showed it just a couple of weeks ago in a regular lecture about cache mapping. So what is the mapping of memory locations to cache locations? Where can a memory cache line end up in the cache, and why is this important, and why is it good to think about that? So this is the problem. We have a memory, main memory, which is nowadays gigabytes, so order 10 to the 9, 10 to the 10 bytes, which is also, of course, organized in cache lines. Whenever you access something, you get the complete cache line, 64-byte or 128-byte aligned cache line. There are many of these cache lines in memory, but there's just few of these cache lines in the cache of the order of megabytes or tens of megabytes. So there's 3 orders of magnitude in size between memory and cache, and the question is, how is the mapping done? Who decides where a certain cache line in memory is mapped to in cache? And since this is such a large discrepancy in sizes, 3 orders of magnitude, there's bound to be some problem. Yeah? The cache is never big enough. Okay, so the easiest way, sorry, I should put it the other way. The mapping is static, which means I always know, if I look at a certain cache line in memory, where in the cache it can go. There's only a couple of possible locations in the cache. This mapping is static. It's an architectural feature of the cache. So if I say, I have this processor which has a cache which is 16-way set associative, then a computer architect knows what I'm talking about, and this says something about where this cache line can go in the cache. This mapping doesn't work that way that I could say have one cache line that can go anywhere. If that were the case, I would have a fully associative cache. One cache line could go anywhere in the cache. That would be the most flexible, but you can't get that, because that would slow down the cache so much it wouldn't be useful. Okay, so we make some compromises, and these compromises lead to some bad effects sometimes, and one of these bad effects is cache thrashing. So if you don't do it right, for example, if you happen to choose the leading dimensions of your multidimensional arrays to be powers of 2, it may happen that performance goes down just for these powers of 2 because you evict cache lines earlier than necessary. Or in other words, your effective cache size is not 20 megabytes, but just 2 megabytes, or even less, 64 bytes. Yeah? If you're really bad luck, you can arrange for effective cache size to be just a couple of 100 bytes. Okay, second. Okay, so what's the easiest way to do a mapping of memory locations to cache locations? The easiest way to be hardwired in hardware is a direct mapped cache, which means every memory location can be mapped to exactly one cache location. If I look at an address in memory, it belongs to a 64-byte cache line. I know exactly where this can go in the cache. So this is very easily done. I look at the memory address here. This is a 20-bit memory address. And I want to map it to a 1 kilobyte cache. So I just take the lowest bits of the address and separate it from the higher bits of the address. And the lowest bits of the address tell me exactly the position where this memory location is mapped into the cache. And the higher bits have no significance there. Okay? Which means if I jump through memory with a stride which is equal to the cache size, I always hit the same cache line. I always hit the same position in the cache. If I go through memory with a stride of 1, reading an array 1 by 1, nicely, byte by byte, there's no problem. Because I plow through memory, I'm reading the cache lines in successive order, and they are placed in the cache in successive order, so I can use the full cache. But if I jump through memory with a stride which is equal to the cache size, I'm hitting memory locations which are mapped to exactly the same cache position every single time. So my effective cache size is, okay, it's arguable, but it's 0, effectively. Yeah? I can't use the cache at all. This is the bad thing about direct map caches. But it is easy to implement because all you need to do is separate off the lowest 10 bits in this case. This is your address in the cache. This is where your data goes, period. No decisions to be made, hardwired in the hardware. This is what it looks like. Here we have our memory. We look at memory as being organized in chunks of the cache size. This is our cache. In this particular example, we assume a cache size, for example, of 256 kilobytes, and the main memory size of 1 gigabyte. This is our main memory. We have many of those chunks of 256 kilobytes, 4,000 chunks exactly, and there's just one chunk of cache, and each position in one chunk of the memory here is one cache line. And when I am at a certain position in the memory, I know exactly where this cache line goes. It goes into this position of the cache. If I am at the same position but in a different chunk in memory, I'm hitting the same cache line. And you see immediately that if you go through memory linearly from 0 to n minus 1 and then from n to n minus 1, you cover the complete cache. You're caching cache lines successively. You can use them as they're in the cache, and then they're evicted when new cache lines are coming in. But if you jump through memory in this column, so going from here to here to here to here, you read cache lines that hit the same position in the cache. This is extremely severe cache thrashing. And you're throwing out each cache line once you access the next one. And this is the bad thing about a direct map cache. That's why we usually don't see direct map caches anymore today. And there have been some processes in the past which used that, at least in the lower levels, level 1 cache, for example, but this is not the case anymore. So here in this particular example, we have 4,096 cache lines in this set of cache lines, and they're all mapped to the same cache location. Okay. What can one do to ameliorate this effect, at least a little bit, to make sure this doesn't happen too often? And the invention that ameliorates this effect is a so-called set associative cache. A set associative cache consists of a certain number of so-called sets, and each set contains a very limited number of cache lines. For example, 2, 4, 8, 16. And this number is called M. If I have an M-way set associative cache, it means each set has M cache lines. So the size of the cache is M times N, and each memory location, which has an address of I, can be mapped to M possible cache locations, not just one location. In a direct map cache, I have one exact location where the cache line can go. In an M-way associative cache, I have M possible locations. And these are M locations which belong to the same set. That's the definition of a cache set. Yeah? A cache set is a collection of cache lines where a specific memory location may go. And there's a choice. If there's 8 elements, 8 cache lines in the set, each memory location can go to 8 different cache lines. Okay, here's an example for a 2-way set associative cache. So that's our cache, 256 kilobytes again. It's divided in 2 so-called ways. And if you take a certain cache line here and its corresponding cache line in the second way here, these 2 cache lines form a set. This is the set. So this set contains 2 cache lines, and whenever you identify a memory cache line to be loaded into cache, it can go to either of the 2. Okay? The number of sets is the cache size, 256 kilobytes, divided by the cache line size, 64 bytes, divided by the number of ways, this is 2, so we now have 2,048 sets. This is also a number that you get if you type liquid topology minus C. It gives you the number of sets for each cache level. This is meant by the number of sets. Okay, so how do we have to look at the memory address in this case? Now it's separated into 3 fields now. We have an address within a cache line that's the lowest 6 bits, because with 6 bits I can access 64 bytes. Okay, so the lowest 6 bits tell me where each byte goes inside the cache line. This is clear, this is trivial. And then the next 11 bits, because I have 2,048 sets, I can address 2,048 things with 11 bits. The next 11 bits address the set. So if I have an address, I take these 11 bits, which give me the set in which the cache line can go. And these 6 bits give me the position of the byte, which I want to access right now. OK. And then there's the remaining question. If I have to load a cache line to the cache, who decides where the cache line goes? Does it go to the first way or the second way? And this depends on the hardware. There are different strategies to choose from. For example, the hardware could decide put it in a random position. So it just chooses any of the 2 ways randomly, one possible way. Nowadays, we usually have a least recently used strategy, which means the hardware knows which of those 2 cache lines in the set has been least recently used, which is oldest, which one has the oldest data. There's some tag field, some flag that tells us how old is the data here. And then if a new cache line comes in, which has to take one of those 2 places in the set, the oldest one is kicked out. Either written back if it's dirty, if it's modified, or just eliminated if it's not modified. Okay, but this depends on the hardware. It's usually documented how this is done in the hardware. Okay, ideally, I would have a fully associative cache, meaning every cache line in memory could go to any cache line in the cache, which means the set, I would have only one set, and that would extend through the complete cache. But that's not feasible. I wouldn't have any thrashing, but it's not doable, because every time I need to load a cache line, it would have to decide across 4,096 possible cache lines which one is the oldest. This takes time, and this is not feasible. So we want to keep the number of cache lines in the set as low as possible to make the decision easy which one of those should be evicted. Okay. So if I turn up the associativity, the overhead gets larger. You see this with the large caches we have in the L3 cache regime in the modern processors. For example, on a Westmere processor, we have a 16-way associative level 3 cache, but we only have 8 ways in the level 1 and level 2 cache. The faster caches are less associative. We have smaller sets. So here's a picture from the beginning again. We now organize our memory again in chunks. And now we are not using the cache size as a chunk size, but half the cache size, because we're having 2 elements per set, 2 ways. And the cache is also organized in 2 ways. Now, one set is one set of 2 cache lines at the same position in either way. So if I have a certain memory location to be cached, there's a choice. I can put it in any of those 2 positions. And if I access the next memory location, which is the number of cache lines apart, I can take the other one. Of course, if I jump through memory in strides of the cache size, that doesn't help me. Okay? It's still bad, because after the 3rd access, I will be in the thrashing regime. Okay, but it ameliorates the problem. It makes it harder to hit this thrashing effect. Okay, so let's see this using an example. And here we see exactly what's been discussed before. If you have powers of 2 in leading array dimensions, so the first dimension in Fortran, the last dimension in C, and you access these arrays with multiple streams, then it may happen that thrashing occurs. So for example, we have a double position array here, 16,384, so 16K squared. What really matters is the leading dimension, okay, the first dimension. The second one is not so important. And we happen to have a code which goes through this array like this. So I access A of 1, 1, A of 1, 2, A of 1, 3. This could be a stencil code. Yeah? This could be the first iteration, a part of the first iteration of a stencil code, where this is the inner dimension, the 1, and the 1, 2, 3 is the outer dimension or the middle dimension. And I plow through the array like this. And of course, I also access A12, A21, A22, A23, and so on. But I'm doing it 3 streams at a time. You see from the array addresses here that these 3 elements, A11, A12, A13, have the same position inside the cache line. That's not so important. But they also have the same set index. So these three array elements map to the same set in the cache. Now, if I only have two elements in each set, if I only have a two-way set associative cache, and I access these three elements, I've already died the death of thrashing, because after loading this element, I'm fine. After loading the second element, I occupy the second cache line in the set. And then, when I load the third element, one of those two just loaded cache lines has to go away, because there are only two elements in the set. So in this case, if I had a 4-way or 8-way associative cache, I would be fine. Yeah? Because I'm only using 3 cache lines and not 4 or 8 or more. Okay. So this is what happens, or what can happen, if you use powers of 2 in the leading dimension. So okay, let's have a simple example. We have a 2D square lattice. This is not quite a stencil code, but almost. On each lattice point, we have 4 data elements stored. Let's say these are 4 velocities, so we store velocities in 4 directions. If you know lattice Boltzmann, think in terms of lattice Boltzmann. If you don't, just accept it. We have 4 velocity components stored on each lattice point. And we have a loop nest here going through the complete lattice. J goes from 1 to n, I goes from 1 to n. And for each lattice point at ij, we do something to the data. So we calculate some value, ij1 minus value of ij2 plus value of ij3 minus value of ij4. Multiply, add them together, whatever. And here it's all added up. So we do something. We have to access this data to do some arithmetic with it. Okay. Now let's see what happens in a very controlled environment if we put this on a computer and we choose an array size of 16 by 16 by 4. Okay, so this is Fortran. The leading dimension is 1 to 16 here. The 4 is the last dimension that parameterizes our velocity component. And let's assume we have a cache of size 256 bytes. So we have 32 double elements in this cache, very small. It's 2-way associative. So each set has 2 cache lines. And the cache line size is 32 bytes. Okay, so very easy, very controlled. You can easily visualize this. This is the memory layout of our array. Yeah? 111 is the first element, 211, 311, and so on. And when I'm running out of the first velocity component, I start with the data for the second velocity component, 112, 212, and so on. So for the first iteration of my loop, which is I equals 1 and j equals 1, I have to access the velocity of 111, 112, 113, and 114. That's the 4 components I need for doing the first update, the first summation. Okay, so I'm starting. I load 111. And of course, I get a complete cache line, which is 32 bytes. So I get 4 elements. This is my cache. It has 2 ways. So each set has 2 elements. And let's say this cache line, the yellow one, goes into the first entry, the first slot of the first way. OK, then I load 112. I get it here. Very fine. Then I have to load 113. But 113 is a multiple of the cache size apart from 112 and 111. So it maps, of course, to the same set. Since I only have 2 elements in the set, this cache line is loaded to the cache, but the previous cache line here, the yellow one, the oldest one, gets evicted. It's just forgotten. It's not been modified, so it doesn't have to be written back, but it's forgotten. Same holds for the black cache line. So I've done 4 loads. I've loaded 4 cache lines to the cache. 2 of those are still here, but the 2 first ones have already been forgotten because the cache doesn't have enough ways. Each set doesn't have enough entries, just 2-way set associative. And then it gets even worse because now I have loaded my first 4 elements into registers. Of course, I can use them now. I can do the arithmetic, update my summation variable, and then I go to the next lattice side. 211, 212, 213, 214. I start with 211 because that's the first load I do. Okay. That means the first cache line, the cache line which is in the first element of the set, which was the bright blue one, has to go away. second cache line evicted, third, and fourth. So every time I access memory, every time I do a load to memory, I have to get a complete cache line from memory to the cache, every single time. I cannot use any of the cache line, any more of the cache line than the current element. So the cache is essentially useless. Okay? This is cache thrashing. Of course, the performance will go down significantly. You could, for example, have a multi-level cache where the outer level has a higher associativity and the inner level has a lower associativity, so that this kind of effect probably occurs only on the L2 on the L1 level, but the L2 level is associative enough to catch these cache lines. Then you get a performance penalty. You don't drop so much, but it still is a visible effect. Okay, so this has to be avoided by all means. Yeah.
Is it hardware smart enough to get for the second step later to first and then go because for first step you have to do it later than and the second step
It might reorder the loads, probably. I don't know. Yeah. So, good question. But it's still, I mean, you could by doing the right order in the second step, you could probably save 2 accesses, but the other 2 you have to get from memory. Yeah. Well, requests for loads from cache lines are usually queued up in a queue. And of course, there's a specific order to that. The compiler might have reordered these loads. So probably the compiler sees it, but I don't think so. My guess would be that the hardware cannot do anything about that. The hardware sees the cache requests as they come into the queue, and they are requested. They are serviced in this order. Okay, now what can we do? Of course, the problem is this leading dimension. And we have a multiple, when we go from one element to the next, we have a multiple of the cache size that we have to jump across. So why don't we just choose a little bit leading dimension and also second dimension here, which is a little bit different from this very bad power of 2 of 16. So what happens? It doesn't mean, of course, that my problem size has to be 18 by 18 now. I can still work with a 16 by 16 problem size. I just have to leave the last 2 elements of each row empty. Okay, this is additional memory I have to spend. I have to allocate it, but it's very small. It's just a boundary effect. My actual problem size can be the same as before. Okay, what happens now? You see here what the memory layout is now. Since I'm not using 16 times 16, but 18 times 18 elements for this array, I now have a size for each of the subarrays which is longer and especially not a multiple of the cache size. So it extends a little bit into the next chunk here. Same is true for the dark blue, light blue, and black. So they're skewed, they're shifted in relation to each other. And now if I do the first iteration, I have to load 1, 1, 1. I have to load 1, 1, 2. And this is the cache size plus an integer multiple of the cache line size apart from the first cache line. So it can go to a different set. It doesn't really matter which element of the set it goes to. It goes to a different set. That's important. The third one is here, and the fourth one is here. So essentially, I can get away with one set because all those 4 cache lines, with 4 sets, and each set only is occupied with 1 cache line. And then, of course, in the next iteration, I need, I need 2, 1, 1, 2, 1, 2, 2, 1, 3, 2, 1, 4, and they can go to the second set. They're still here, They're still here. So if I access a second element in each of those cache lines, it's still in the cache. So in this particular case, I could get away even with a direct map cache. I wouldn't even need the second entry in the set because I've done this padding. Okay, so that's how you avoid this, yeah?
So it has to be plus 2 because there are 4 constants. So you can't get away with maybe 7.
You could get away, well, this has been engineered, of course. So to make this offset here a multiple of the cache size. If, for example, if you only do the +2 in the first dimension, then you would see the blue cache line beginning here. But when you access 1, 1, 2, you get the complete cache line starting here. And then these two would go to the same set. But the bright blue would then be moved here, and this bright blue and this black would go to the second set. So it would still work in this particular case. Yeah. But you have to take care. It depends on the offset that you have to choose here, and also here probably depends on the cache size and the number of sets you have, and the number of entries in the set. So you have to think about this when you have a specific problem. What's my required padding that I have to use? In practice, if you're too lazy to figure this out in your head, you can just try it. Yeah? Usually, if you go away from the power of 2 in the first dimension, you can try a couple of values, and then you see what's going on. As we stressed multiple times, it's always a good idea, if you have a loop kernel that you want to benchmark and understand, to tune the problem size. Not just hit a specific problem size because that's what you're interested in, and then try to think about that, but try to tune the problem size, if possible. Because then you hit these pathological points. Yeah? And it's not just about cache thrashing. There are other hardware features that you can hit that probably make a problem in some codes. Okay, yeah. That wouldn't help because it wouldn't change the access pattern. Yeah, the data access pattern wouldn't change. It might help in terms of Pmax, low-level performance, to have two accumulation variables, but not in terms of data access. Okay, so much for the cache thrashing feature and the cache mapping issues. Okay, now let's continue. Now this next part until hopefully lunch, we want to tell you a little bit more about optimal utilization of parallel resources. And of course, as you know now, there are lots of parallel resources in modern compute nodes, starting at the core level down to the memory. And of course, you have parallel computers which have many, many nodes. We want to highlight actually two specific problems or features, which is SIMD. You've heard a lot about SIMD already. We want to dig a little bit deeper, and proper programming for CC-NUMA page placement. So how do we make sure that the memory ends up in the NUMA domain where you want it to be, where it has to be? There's also a part about simultaneous multithreading, but I think we will skip that for brevity. Okay, so single instruction, multiple data processing. When we introduced the modeling yesterday, we already told you how to deal with AVX, for instance, so you know the principal limitations of modern processors when it comes to executing AVX code. So there's on a modern Sandy Bridge or Ivy Bridge processor, you can do one full-width AVX load and half a store per cycle. You can do one full-width AVX multiply, one full-width AVX add, and so on. But there's a little bit more to be said about this. Here's again our overview slide on vectorization and SIMD processing. So this is scalar execution. We only use the lowest slot in the vector registers. And if your code cannot be vectorized, if your code cannot use SIMD processing because there's something that blocks this utilization of parallel resources, you might have some dependency in your loop or some if condition that prevents vectorization, the compiler will always generate code that only uses the lowest bit, the lowest entry in these registers. This could be a 64-bit double. It could also be a 32-bit float. And there are, of course, also integer variants of these instructions. Okay, this is scalar execution. This is vectorized execution. You use the full width. And in this case, we have 4 wide SIMD units in double precision, AVX. So we can do 4 additions at the same time. So that's the basic thinking, again, behind SIMD. Here we see what the compiler has to do. And this is strictly something the compiler has to do. Some people try to do this by hand to help the compiler figure out that it should do SIMD, but the compiler should really be left on its own with this. Yeah? You can help the compiler in several ways. We come to that. But these simple transformations to make SIMD possible should really be done by the compiler. So this is our loop. We add 2 arrays and store to the third. That's exactly the stream add benchmark. We'll see this later in the demo. And the first thing we have to do is, or the compiler has to do, is recognize that this is really something that can be done independently for every loop iteration. Every loop iteration is independent of the next. So no data dependencies, no control dependencies, no conditions, nothing. Okay, so we can just unroll the loop. Instead of going from 0 to n minus 1, we go from 0 to n minus 1 in steps of 4. Of course, we have to care about the case where the loop length is not a multiple of 4. We omit this. Okay, the compiler has to include some remainder loop handling. That's also a big point for not doing it on your own. Because if you try to do this on your own, you have to handle these remainder loops, which makes the code really clumsy. And you have to put in multiple versions of your loop to make this happen. So try to make the compiler do it. Okay, this is a prerequisite for looking at the loop in the SIMD way. And now we can identify exactly what we need. So we need a load to b of I plus 1, I plus 2, I plus 3. A load to a of I to I plus 3, and a load to c of I to I plus 3. These are consecutive in memory. So these accesses are SIMD load, and a SIMD store for C. So the compiler can just issue the corresponding vectorized instructions. A of I goes to R0. In this case, it's a vectorized load. So we mean the three elements that come after A of I plus A of I itself. The same is done for B of I. And then we can do the add. V64 add is just a mnemonic symbol for doing a 64-bit vectorized add. And we store the result in R2. And then we store R2 back to memory using a store instruction, using the address C of I. And then, of course, we need to advance the loop counter by the SIMD size, in this case 4. And, of course, there's the branch to check whether we have reached the end of the loop. Okay, so that's what the compiler has to do in this simple case for vectorizing the loop. And, of course, if the compiler recognizes that all this is independent, it will do this easily. Even the GNU compiler can do this, so it's fine. Now, what can prevent vectorization? What kind of code do I have to write? Or what kind of information do I have to hide from the compiler so the compiler must assume that's not possible? The worst kind of thing that can happen is like this. This is a loop from 0 to n minus 1, and I'm doing A of I equals A of I minus 1 times S. Which means every multiplication in this loop depends on the previous multiplication to be completed. So I have to wait for this multiply in loop index I to be complete before I can even start the next multiply. Because the output from one multiply is taken as the input for the next multiply. Which means this loop will run at a maximum performance of, what's the performance? In flops per cycle? How many flops per cycle will I have for this loop? Sorry? No, much less. How long does a multiplication take? 5 cycles. So when I do the multiply here, I can only start it when the last multiply, the previous one, has been completed. Sorry? 1/5, exactly. Sorry? Very good. Okay, so 1/5, which means one multiplication every 5 cycles. If we have a 1 gigahertz processor, we run at 200 megaflops. Okay, if there's no other bottleneck, such as getting the data from main memory, but we will see probably something about this later. Okay, so this cannot be vectorized, of course, because if you have dependency in the iterations, it's not parallel, it's inherently sequential. It's so sequential that not even the pipelining works. Okay, but even if we have a seemingly parallel code like this one, this is exactly the code from the previous slide. Let's assume we have this code, this loop inside a subroutine, scale shift, and this function gets the arrays as pointers to doubles and the array length n. So it seems like this should be fine. Yeah? Because all loop iterations are independent, why should the compiler not vectorize this loop? If you give the compiler this loop, it will refrain from vectorizing. And if you switch on the compiler diagnostics, it will tell you vectorization impossible, loop dependence or data dependence. Why is that? You as a programmer probably know that the arrays A, B, and C do never overlap. There could be different parts of a big array, or there could be different physical representations of something, so you know they don't overlap, but the compiler doesn't. And the C and C++ language allows arrays to overlap in any possible way. Now, if these arrays are allowed to overlap, theoretically, the compiler has to take that into account. So probably, the compiler may think probably A, so the base address of A, points to C of -1. And B points to C of -2. So they overlap almost perfectly. Then what's actually written here is not C equals A plus B, it's C of I equals C of I minus 1 plus C of I minus 2. And now we return to the previous problem. There's a strong dependency. These iterations are not independent, so there's no way this can be vectorized. Okay? And there are two problems in one. The compiler must assume that this may be the case, so the compiler cannot vectorize. It must also make sure that all the loads and stores that are necessary to execute this loop are in the correct order. So there's no way the compiler can reorder loads and stores. If it does a load in advance that actually comes later in the code, it might incur wrong results. So the compiler must exactly translate this loop to assembly language in exactly the order in which it is written in the high-level language. So as you know, compilers do a lot of reordering, a lot of optimizations in the instruction flow. That's all not possible here. Of course, you might know that these arrays don't overlap, especially not in this toxic case. So you can tell the compiler, my arrays don't overlap. And you can tell it, for example, with the Intel compiler with a switch -f_no alias. You can just put it in the command line of the compiler. And if you say -f_no alias, then the compiler can assume there's no pointer aliasing, no overlapping arrays. And that will enable vectorization for these arrays and also other optimizations like reordering of loads and stores. Yeah? In Fortran, it can't happen because in Fortran, arrays are not allowed to overlap. You cannot have array aliasing in Fortran unless, there's one exception, if you use pointers. That's why pointer code, Fortran pointer code, is sometimes slower than code that uses plain arrays or allocatables. Because the compiler, if you give it a function that takes two pointers, real Fortran pointers, must assume they may overlap. And that's why also the Fortran compiler, the Intel Fortran compiler, has the same switch. Yeah.
See, how can this parallelization ever happen? Because usually you get your arrays function calls, so it will never happen.
Exactly, that's the magic switch. That's what fills, I would say, 95% of the gap between a C version of a code and a Fortran version. This is the point. Yeah? This is the golden switch. Yeah. Yeah, exactly. In C99, you can put the restrict keyword between the star and the variable, I think. So it's double star restrict A. And that tells the compiler for this specific array, it doesn't overlap. So you can be a little bit more specific. This is for the complete compilation unit. That might be a big hammer. Okay, probably you shouldn't lie, of course. If you lie, then it will be wrong code. But the restrict keyword in C99 can be used in front of the identifiers A, B, and C, and then the compiler is allowed to assume no overlapping. That's right. I think we have it in new versions of the slide. Just forgotten. So this is really a magic switch. We have many occasions where people come to us, they have a C or C++ code, and they do many optimizations, and it doesn't really help. And then we switch on f_no alias, and it all works like a charm. Unfortunately, the restrict keyword is not defined for C++. Some compilers allow it anyway. You can switch it on, but it's not in the C++ standard. It's only for C. Okay, so keep that in mind. If you know that there's no pointer aliasing in your program, which is true for many programs, of course, then just switch it on. And you will see in many cases that performance will go up. Okay, so much for the basics of SIMD and how to help the compiler to make it possible. Unfortunately, we have to dive in a little bit more detail to tell you or to teach you how to deal with this on a day-to-day basis. And it does include a little bit of assembly language. You may refrain from doing this, but you will see it's not that hard. And it's not about writing code in assembly language. It's about judging what the compiler did and whether what it did is really useful, or whether it has some problems that it just didn't report. Okay. Yeah?
Maybe we show the code from yesterday even because of missing vectorization. And there's also an example of how to use the restrict key.
Can you do it?
So yesterday we had a discussion with the participants that he has also a stencil code and doesn't get right.
Moment. Mikrofon.
It seems to be really slow. So that means here we have an example for the use of the restrict keyword. So here, this was done very well. So the restrict keyword here tells us that, or tells the compiler that those 3 pointers do not overlap. And this is actually a stencil code, very similar to the one we have seen in our lecture, but this is a stencil code which has 2 arrays on the right-hand side, W0, where we only load 1 element, and W1, where we access a second-order stencil. So we not only go to k plus minus 1, but also to k plus minus 2 and j plus minus 1. So this is not only touching 3 successive layers, but 5 successive layers. And we write back to another array. So here you can see restrict, 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 so perfect. No dependency assumed by the compiler, but the compiler didn't vectorize. Any idea why? The if statement. Enjoy. The if statement. We have an if statement here. Who can tell what this if statement does? I have seen this similar code at 2 occasions, in 2 different contexts as well. I'll tell you where. What does the if statement? Yeah, this is boundary handling. I have seen such code also in a summer school last year, where master students did program a CFD solver and did always do their boundary handling by those if statements. You can just get rid by starting at I equal 2 and ending at nx minus 2. So you can just remove the if statement by adapting the loop boundaries. After doing that, compiler did vectorize, and single core performance did increase by a factor of 3. Okay, so, oh yeah. Now I could ask you to do a performance model. But there was another thing we have seen. So parallelization was fine with Pragma OMP parallel, but performance did not scale to the second socket. And the problem here was that the initialization, here's the initialization loop, that the initialization loop was not parallelized, so all the data was on one socket. We didn't do that. Okay. Okay, I think that's it. So here you can, okay, with memory alignment, this is also what comes next. Okay, so this is a nice code, and if there's some time, we can do we can join to do performance modeling to get an estimate.
Is this on the website as well?
Would that be fine? To put the code on the website? Okay. Okay, so this is a nice example, and you can do derive the layer condition and things like that when you're back home.